So our next and last speaker today is Aritro Mukherjee, Dynamical Quantum State Reduction Models via Spontaneous Unitarity Violation. The floor is yours.
Thanks a lot to the organizers, and thanks a lot for all of you just being here. I'm Aritro Mukherjee, and today I shall be talking about my exciting research on dynamical quantum state reduction models using spontaneous unitary violations. I'm at the University of Amsterdam in the group of Jasper van Bezel. So we start off with the standard axiomatics in quantum mechanics, where quantum states live in a Hilbert space, and these states can change through unitary dynamics or via the projection postulate. So unitary dynamics comes about because of interactions or something like any sort of interactions, and generically this will lead to entanglement, and indeed on the block hypersphere this will just lead to rabbi oscillations. Whereas the projective map, the projection postulate, is induced, quote unquote, according to Neumann and the old quantum people, via a macroscopic measurement device. It is an instantaneous map, and this collapses, quote unquote, from a completely entangled state to a pure state which is not entangled. So when does one stop using unitary evolution, and when does one start using the projection postulate? This indeed leads us to the quantum measurement problem, if you assume that everything is quantum mechanical. And there are various ways in and there are various ways out using time-honored ways, interpretations, decoherence approaches, as well as objective collapse models, which this presentation is all about. So what are objective collapse theories? It has a long history, as you can see, a very rich history, where people have argued that they should modify Schrödinger dynamics based on gravity, changes in the uncertainty principle, and so on and so forth. But the main point is that you want to keep your microscopic dynamics unchanged. Entanglement should remain in the microscopics, while at the macroscopic level, entanglement should die off. So there should be, macroscopic superpositions should die off. So there should be a quantum to classical crossover, quote unquote. Further, if you utilize one of these theories and you model measurement, you should also get Born's rules. So what are the modifications that we do consider? Turns out that there are some necessary conditions, which was shown in this paper here, and Lotte Mertens just gave a talk about it. And these necessary conditions include that your dynamics has to be many to one and nonlinear, where here it's just a cartoon, not to be taken very seriously. But of course, in a measurement, it has to be many to one and nonlinear, because you start off with an entangled state, and then you end up with a pure state. Or indeed, the final result of your measurement depends on the initial state. So it has to be nonlinear. Further, it has been shown that it has to be non-unitary, which would break time inversion symmetry and lead to irreversible dynamics. It also has to be stochastic, because that is the hallmark of quantum mechanics. And apart from these necessary conditions, the theory that I shall be showing is not instantaneous, but dynamical theory. If you're concerned about so many modifications, I'd like to remind you, for the last 100 years, using Neumann's projective map, we have actually been doing all of these things. It's nonlinear, time inversion broken, and it's stochastic. But of course, we've been doing it lazily and instantaneously by hand. So I now come to the work that we've been doing, which is on spontaneous unitary violations. And this is the modified Schrödinger equation that we are working with. So that is just the standard part, and that is the modified part, where you have this nonlinear operator G. It is nonlinear because it depends on the state only at time t and not at times before, so no memory. And further, there is this stochastic element psi. This coefficient up front has an extra factor of I, which makes it explicitly non-unitary. The n and epsilon are number of particles and the symmetry rating parameter. So how does it work? It works by recognizing that time inversion symmetry is like any other symmetry in the world, which can be broken. And as Lotte Mertens just showed, the usual Schrödinger dynamics is highly susceptible, infinitely susceptible to a non-unitary perturbation like this. So then that means that there exists these non-commuting limits, which is a mathematical hallmark of phase transitions. And if you take the limit in this way, where the non-unitary perturbation which is coming about because of some macroscopic modification, is first taken to 0, and then you take the thermodynamic limit. You end up with entanglement, with persistent entanglement. So this is the quantum regime, whereas once you change your phase, quote unquote, you take the limits in an opposite sense. You take the thermodynamic limit first, and then the symmetry rating term goes to 0. You find a localized classical-like state, like a chair. So how do we do a quantum measurement with this model? We just have to identify that state, psi of t. It represents the full state which is undergoing measurement. So this includes the system, the apparatus, and if you want, a local back around it, which undergoes a projective measurement. And further, the states after the dynamics at time tends to infinity are the macroscopic pointer states, such as the states you would find in a readout of an actual measurement machine. And we don't want those to be in entangled, we don't want those to be in superposition. Further, these final states are also the symmetry broken states, time inversion symmetry broken states. And in this way, you can write down a prescription for measurement without actually tracing the path. So just the modified dynamics, so I've removed the standard part and taken the coefficients inside, and the i's cancel out, and I have this. And I just argued that the states look like this, where the basis vectors are the macroscopic pointer states, which at the end of the dynamics should not have any superposition. And I also suppress these guys inside. So turns out that normalization is a big issue in these kind of class of models, but there is a general prescription that one can write down for a class of models with this particular property, which is that the quantum stochastic Ito correction term, or the quadratic variation term, is 0, almost surely. This means that then you can write down these normalized equations, taking your original G, and just subtracting a geometrical factor there. So let's quickly discuss the two-state system, which was also discussed by Lottie. That's the generator, okay? And this generator here does not conserve the norm, as was asked by people in the audience. So this generator consists of these Pauli matrices, the usual ones, and that's an expectation value, which would be nonlinear, which is defined here, and that's your stochastic variable. J and K are these constants up front. So turns out we can use the normalization prescription, and we get this new generator here, and the norm is now preserved, and this is your complete Markovian limit, because from one time step you can go to the next, where this guy I just showed you is the modified equation, and that is your noise dynamics written in Ito formulation for a general continuous noise, where dWt is the Wiener measure. So now we would like to compare it with the well-known stochastic Schrödinger equation. And this equation has, again, a huge history, and it has many names: quantum state diffusion, primary state diffusion. I'll just call it the stochastic Schrödinger equation. This equation is the mathematical basis for many other objective collapse models. So that's the SSE equation up front, up top, and there's our equation. So the elephant in the room is that you have the dt over there, so that is the drift term, and that is your dWt, the Wiener measure, so that is your diffusion term. But in the SUV model, there is no diffusion term. Everything is inside the drift. So that's the first distinction, which means, of course, that I can formally write down this guy with the partial derivative. And this also means that this guy on top, the SSE model, is continuous but not differentiable temporally. But this guy is indeed differentiable temporally and continuous, of course. Further, this guy, the infinitesimal Wiener measure, is Gaussian white noise times dt, where Gaussian white noise is not correlated, whereas in our equations, psi, the noise, is in a general correlated or a colored noise. Further, historically, this nonlinear factor up here was obtained from a different set of equations by Gersonov transformation, and these two equations do not have the same statistics, whereas I just showed you that in our equations, this nonlinear term comes about because of a geometric correction, and the statistics do not change between the two equations. This further nonlinearity up there are not equivalent, because if you try to complete the squares, you will find extra factors of 2 and so on. So this SUV and the SSE model are not equivalent. This here is an illustration of the actual numerics for the SSE model, and we are just computing the probability amplitude, where in black is the SSE model, and in blue and red are the SUV models. One is normalized using the normalization prescription, and the other is numerically normalized every time step. And we see that they're right on top of each other. Dynamics do not change, statistics do not change. So now we move on to the flow models. First I would like to talk about this limit, which is the strong projective measurement limit. So from various arguments in the literature, one notes that collapse should happen faster and faster for more macroscopic devices, or for more macroscopic superpositions, just for consistency. That means that the experimentalist actually has a lot of freedom. They can tune their device to be as large as they want, which also further means then in the first approximation, the collapse happens really fast and the noise has hardly changed. The stochastic component has hardly changed. Which means that in this approximation, the correlation time, the noise correlation is almost infinite, and the change in the noise is almost zero. And together with these two equations, we find a complete Markovian limit of these equations. So we can now do what the two-state measurement that Lotte Mertens was talking about. This is the same equation written in just like in a different way. And it was shown that like Born's rule emerges in this limit when you take j and k and set them to 1. And when you take your random variable from a uniform distribution between -1 and 1 once every measurement. And it does not change during the measurement. This is first approximation. This is the model that Lotte showed, and you can derive this guy from the previous model by using the usual block-sphere transformation. And that is what the model looks like on the block sphere, and we see these two flows, and this line which is separating the flows. And this line is called the separatrix, and it also separates the phase space of the random variable into two parts, such that depending on your initial state and the random variable which you sample, you're either going to move up or you're going to move down. And this follows Born's rules. We can generalize this to n states by separating, well, basically dividing your phase space of your random variable now into n parts, right? And these would require lines, which the equations of which are given over there. And the unnormalized generator then has this particular form, where j's, I just argued that these are the macroscopic pointer states which you don't want them to be superposed. You want them to collapse. And this guy f is a highly nonlinear factor, which is also redundant, and it is the same for all of the j's. And this is the expression for that. So this here is some numerics. There's a three-state model, and there are the two lines which separate the flows. And you can see that starting from an initial state somewhere, you will always flow to either 0, 1, or 2. Here is more numerics for the four-state case now, and in black are Born's rules from standard quantum mechanics, whereas in yellow are the SUV model statistics by doing many, many iterations of the previous model shown. There's another way that we can generalize in a hierarchical fashion, and the key idea is that we use this two-state collapse process, and well, we divide our entire state space into two equal halves, and then we undergo some sort of we undergo a two-state dynamical quantum state reduction or collapse process using the two-state model, and then we go to another level where again we divide it and again, and such that at the end we end up with just one final measured state. So this implies that there are well-separated two-state collapse processes now in this particular generalization, with control parameter delta which is really small. And this sort of collapse, instead of being induced by one component, will be induced by log n number of stochastic components with base 2. And the nice thing about this kind of generalization is that there's no redundant factor anymore. There's no crazy nonlinear factor anymore. And this is what the equations will look like, the generator. So that's super complicated, but let me just go through it quickly. J's are the macroscopic pointer states, which you don't want them to be superposed at the end of the dynamics. Delta is the hierarchy parameter. Theta is a sign matrix, which is given by this particular expression here. And these guys are the marginal probabilities which are defined here. And of course, delta is smaller, much smaller than 1. We can take the continuum limit of this model pretty nicely. Everything almost works out. And this here is the generator of time evolution in the continuous case, where we have the, of course, PVM, the projective value measure, and this guy is the stochastic field now. It is updated to a stochastic field on all x's, which are your pointers, basically. And it has this particular expression here, with deltas being the hierarchy parameter, and then these thetas are this continuous version of this sign matrix. And we're still working on making this more precise. Also, this pi here resembles a propagator, and there is an expectation value outside it. Pi is given by this particular expression here, with the thetas being the sign matrices. And this sum here goes up to a factor of gamma. And this gamma is a sort of UV cutoff. So let me just remind you, this sum would go up to the number of levels that you have. So this means that this gamma, this factor, the maximum sum that you have, has something to do with the resolution of your measurement. And thus it is like some sort of a UV cutoff, how resolved you can have it. This is some statistics, some numerics for this model, where again in black we see Born's rule from standard quantum mechanics and the projection postulate, and in yellow we have this SUV model statistics for many iterations, for 40,000 iterations, with the small parameter delta being 0.25. And this gets better and better and closer to Born's rule as you think your delta parameter to be smaller and smaller. With this, I would like to conclude. And the conclusion is that I hope I've shown you this class of SUV models which lead to collapse of the wave function or state reduction. It is based on this physical principle of spontaneous symmetry breaking, but in this case we are breaking unitarity and leading to irreversible dynamics. Born's rule emerges, as was shown by Lottie as well, and the statistics that you saw in these models. I hope I've argued that this class of models is not equivalent to the well-known class of stochastic Schrodinger equation models. And I've also shown that this model can be generalized to n states and a continuum. Manuscripts are under preparation. Stay tuned. That's my email address. And here, this picture is this pretty picture. You can see a 16-state collapse into one state. And with that, thanks a lot.
We have a bit of time for questions, so right at the end there.
Yes, it's also a question to Lotte because she has the same ideas. So you invoke symmetry breaking and so that kind of thing. But if you just look at statistical mechanics, you get symmetry breaking and phase transition without any supplementary or whatever terms. It happens by itself. It's already built in the quantum system. So actually, you don't. If you just want symmetry breaking and etc., you don't need to do that. You just have to, use the same tools as this. Okay, you have to go maybe to infinity limits and things like that. But it seems to me that you take a hammer, but there is no point because it's already there.
So in my understanding, there's no condensed matter model that you can give me which you take, you lower it down to low temperatures, you get a critical state, and then from that critical state, such as a ferromagnet which can point in all particular directions, why is one direction chosen? That is the symmetry breaking principle, right?
Yes, but
so what model would take us there?
It's a random result, but okay. But
so are you saying that this kind of transition should be instantaneous? No, right?
No. So there are various ways to do that. I can refer you to a paper by Roger Balian, for instance, who is a statistical physicist in France. And he makes a full calculation and he gets basically, for instance, just
so then he must be utilizing
statistical mechanics. that is the issue for me. That it's a question of taking or not taking the infinity limit. So if you don't want to take the infinity limit, you have to do all kind of subtle approximation, and this is where you can get phase transition. Now, if you take the infinity limit, you get the phase transition for free, and they are, abrupt, and you can get different phases. So, for instance, just coexisting phases is impossible as long as you stay linear and finite. But if you keep quantum mechanics and go to the infinity limit, you can get different phases. This is well known in statistical physics. So I don't really understand why you do all that.
Well,
why the result is already there.
This result, does it include taking some sort of trace? Or taking, removing the environment?
You have to take the trace as long as you remain finite. But if you go to the infinite limit for your side of your system...
So you're saying that in the infinite limit, without taking a trace, with just unitary dynamics,
no, in the infinite limit, unitary breaks down. This is a theorem by von Neumann, 1939. If you admit to go to the infinite limit, then you lose unitarity.
Which infinite are you talking about in this point?
The infinite is the number of particles or the number of degrees of freedom, as you wish.
So you're saying that just usual quantum mechanics in infinite Fock space or Hilbert space?
It's a paper by von Neumann in 1939. I gave the reference and I can give it again. Yes?
Your reference just mentions that in the infinite limit, you get sectorization, right? That is not the same thing as non-unitary behavior.
Yes. So you lose unitary in the unitarity in the infinite limit. This was shown that it's a long paper, but okay, it's just mathematics, and so then you have to interpret that, but what I claim, and I reclaim, I told that, and I told you that, if you take this infinite limit, you break unitarity without doing anything else. You don't need these terms.
Okay,
it happens.
Thank you so much.
Thank you for your thank you for your very enthusiastic talk. We already discussed some of this, but I think it's very important that we share it. As I told you, Bertlev Duer and Angelo Bassi showed that if you assume norm-preservation and no signaling, you will get their collapse model, the SSE. So my naive guess is that your equation is allowing for superluminal signaling. It's very important, and maybe suppose it does. Are you okay with that?
I'm not okay with that, number one. And number two, yes, I'm still computing the master equations.
Yeah, but master equations, you don't have to do that. If you just see the Bassi-Duer paper, it will tell you that if you assume no signaling, you will get the dW term. You cannot avoid it. So if you set dW to 0, it already sort of show, unless I'm missing something.
Yes, so I think so one limit of this guy.
Yeah, you are the expert, you should come in.
I have a comment.
I may be wrong, so please correct me. I was looking for you.
Yeah, I fully agree with Tiki, but I also agree with what is your first name?
Aritro.
Yeah, with you. That the general requirement is to have a linear master equation. It is more general than the condition proved by Bassi and Duer.
Okay.
Once you get the master equation and you see it is linear, then you win the game. If it is not linear, then you lost it.
Yeah.
But still, it's an open issue.
Yeah, so this question is really relevant. I'm still working on the master equations, and it will be more complicated because of this extra noise here. It should end up being non-Markovian, and then you have to take different limits to see what happens in the Markovian limit. So it's not a trivial question.
I just wanted to make a little observation.
Yes.
Typically quantum measurement is like stirring a rock. Atom arrives and it makes ionization rot.
Sorry?
Ionization rot, it reads just point on the photographic screen.
Yes.
And such a process has nothing to do with spontaneous breakdown. and you can talk to any experimental colleagues. A typical quantum measurement does not include this kind of meta state.
Can you prove that?
States.
Can you prove this statement?
Pardon? Yeah, just you take nuclear immersion, okay?
Sorry?
Nuclear immersion. It's cosmic ray arrives and it leaves a track. And in all these typical quantum measurement processes, they don't look like spontaneous breakdown. That's a fact. They don't look like this. So this is my observation. I had a very similar idea with yours 2 years ago, but then I started to talk with my experimental colleagues. The first thing they told me that, look, experimental devices are not in metastable state. In the case, Wilson cloud, double chamber is like this. But in most of measurement devices, experimental devices are in stable state, absolutely stable state. And then first electron, atoms, protons arrive and leave stripes, leave the coin, ionization block. And these don't look like this kind of process you have been studying. I had so but then I had to change my mind actually completely.
See, let me ask you a question. Let's think about a particle which is moving in your box, right? Pardon me? Let's think about a particle which is actually moving in your box, right? Yeah. So this particle is microscopic, but as it gets more and more entangled, there's a projective measurement, quote unquote, because of macroscopic modifications to quantum mechanics. Then, if this is true, if because of macroscopic because of Penrose's argument as well, right? Like, if you move from the microscopic world to the macroscopic world, does quantum mechanics remain the same or not? Of course not, because we are localized people.
So it looks like violet if you study, think about microscopic system of your interest. But if you include everything, experimental device, and then everything else, environment.
Yeah.
And then Unitary looks like violet, but it's a different question. Because you cannot use the notion of Unitary you are accustomed to studying isolated microscopic systems.
No, we're not.
You cannot use the same language. So this is what I thought. I have ideas very similar to yours, but then I have to change my mind actually. It's like this.
Thank you, unless there's another question. I think we'll call it a day and thank us. Oh, hold on, there is a quick question. Well, one more. So keep it short.
Okay, quick question. You formulate everything in terms of the wave function, psi.
Right.
But I'm wondering, whenever you have stochasticity or irreversibility that you introduce, don't you have to go from the wave function to density matrix?
Right. So this question has like many different questions inside. It has been argued in the literature. Okay. It has been argued in the literature that like you would want for a nice collapse process to be defined at the level of the state first, and then you obtain the density matrix. This is true because at the level of the state, the uncertainty is just quantum mechanical uncertainty. But at the level of the density matrices, not only do you have the quantum mechanical uncertainty, but you also have epistemic sort of uncertainties, which are coming about just because of classical mixtures, right? So if there is a collapse process which happens because of nature and not because of environment-related decoherence effects or other ways of like averaging out stuff, then one would have to define it at the level of the state.
And with that, let us thank our speaker.